Hello, my name is Carsten, OZ9AAR Radio. This video is about my new device, the dual RF head USB device, how you use it and how you calibrate it. First, the dual RF head USB is a spin-off of my dual RF head device. If you go to my web page, moonbounce.dk, you will find information about many things, but the dual RF head USB and the dual RF head are both there. The dual RF head is a device that will measure two RF inputs, channel A and B. It has a logarithmic amplifier, and it will deliver an analog voltage that is linear with the change in dB on the inputs. More on that in a few seconds. As I said, this is the original dual RF head, which delivered analog voltages out. It is primarily used for monitoring power amplifiers, sometimes remotely. Together with my REPAM device, you can monitor power amplifiers using network and stuff like that. There are more information on the web page under the REPAM module. This is just to give you an idea of what the REPAM or what the dual RF head comes from. As I said, the dual RF head USB, which I'm going to talk about in this video, is basically the same front end as the original dual RF head. The difference is that the original dual RF head had analog outputs that would tell you how much power you applied on the RF inputs. The dual RF head USB has, instead of the analog output, it has a USB-C connector where you can connect it to a PC and you can get the data directly into an application, or you can use the data in your own application in Node-RED or whatever you want to use for monitoring. Dual RF head USB is an open design. You can produce your own boards if you want. On the web page, the schematics, the bill of material, and shortly the Gerber files for the PCB will be available. You can download it and you can produce your own boards. The hex file for the microcontroller will also be available, so you can download that into the controller. I made a simple PC tool that you use for showing the data from the dual RF head. It can calibrate the dual RF head, and it can also download or upload new firmware versions to the device if they become available. So this is the only tool you need at least to get going. It will show the power in both dBm or watts, and as I said, the project is available, will be available with source code and everything, so you can make a specific version for your own use, or you can change things if you want, and so on. You can also use the data from the dual RF head directly. It is simply a string, ASCII string, that is sent to the PC around 25 times a second. You will get a string with the version number of the firmware. You will get the forward power. This is the average power. There is a filter running so that this is updated a couple of times a second. You will see the peak power measured. This will reset after about 2 seconds. You got reflected power, peak reflected power, and you got the calculated SWR. You also get the forward and reflected power in dBm. if you would rather use that in your program. And you get the raw values that are measured from the logarithmic amplifier. It's an ADL 5519, and it also shows you the analog voltages, the raw analog voltages, if you want to use that for whatever purpose in your own system. The temperature of the logarithmic amplifier is also shown. If you want to do something high precision, you can use the temperature to correct for small temperature variations. Although they are very, very small, but the value is there, so you can use it if you want. The end of the string has a 16-bit CRC value. This is just so that you can verify that you got the correct data and you didn't see any any noise or anything wrong in your decoding. This is how the data looks in a normal serial terminal program using the device as a serial port. Now, as I said, the dual RF head USB present itself as a serial port using the USB-C connector. The device has the ADL 5519 logarithmic amplifier. It has a microcontroller, some analog precision references, and it has an FTDI USB to serial device. This means that you don't have to install any drivers or anything on your PC, as you probably already have FTDI drivers for a lot of other things, so it should be pretty easy. The PCB is a 0.8 millimeter two-sided PCB only. I think this is pretty much, as I said, go into the webpage moonbounce.dk and look around, and you will find the dual RF head, and you'll also find the REPAM device, which is a device that, as I said, can monitor power amplifiers and stuff like that. So with that out of the way, let me find, I have just one thing. This is the dual RF head, the original one, which delivers the analog outputs A and B, and also a difference output, but that's not often used, P and N, but out A and out B are simply analog voltages. The logarithmic amplifier, just a little bit of background. When you apply RF to one of the inputs, it covers from minus around 50 to plus 10 dBm, from 10 megahertz to 8 or 10 gigahertz. It's specified to 8 gigahertz, but it's also usable up to 10 gigahertz, although the response rolls off a bit, so you will have around around 3 dB less response compared to the lower frequencies, but as you calibrate it, it doesn't matter. It will work just fine anyway. But just to give you an idea, the logarithmic amplifier delivers an analog voltage that depends on the input RF, and it is reversed so that a high voltage is a low input value and a low analog value is a high power input. It's just to give you an idea, because in short we are going to calibrate the device, and you need to understand that the response is negative. You see it here on a graph. This is a prototype measured at 432 megahertz. The same for the same prototype at 3 gigahertz, the values. But if you look on the graph, you see that the high voltages, in this case 1.6 volts, corresponds to around minus 40 dBm, going up to around 600 millivolts, which is 5 dBm. And the two channels are quite similar, and the slope is, as you see, very linear. The device is, the ADL 5519 is a very nice device. It's also expensive, but the specifications of it are pretty good, and on the web page, on the Moonbounce DK web page, you can see the data sheets and so on for the chip, and you can see what it is you get. You get approximately minus 22 millivolts per dB. So if the output voltage drops 22 millivolts, you know that the RF input is 1 dB higher than it was previously. And if you see 220 millivolts increase, you know that the power has gone up by 10 dBs and so on. So this is just a small theory about how the logarithmic amplifier works in this setup. On the web page, Moonbounce DK, under the dual RF head USB, there will be a link where you can download a PC tool. It is described in here shortly what it can do and so on, and I will show you how that works now. You download the program from the web page, and there's no installation. There's only a single exe file, executable file, running under Windows. And you just copy the exe file into a folder and double click it, and it starts. There's no installation. It does not change anything in your registry or anything at all. It is just an exe file. There are no separate DLL files or anything you need to take care of. Everything is contained in the exe file. All my software applications are like that, available on the website. So you just start the program, and in the folder where you start the program, it will create a configuration file where it will keep the settings that you apply for the program. You can shrink the window so you only have the bar graph, or you can have both the dBm and the watt output. The first thing we're going to do is I already connected the dual RF head USB to the PC, and I know that it is sitting on COM5. So as the first thing, I want to enable it, and we get data. You see there is a counter down here. This is the number of frames we are receiving. We are incoming data from COM5, and we have 0 watts. And you can also, if you click on either of these, you will change from watt to dBm if you want that. It depends on how you want to see it. There is a details tab. It will show you the number. This is the total number of conversions that is done in the device, version of the firmware, temperature, forward power and forward peak power in watts and in dBm, and the raw voltages measured at the device. In settings, as I said, you can the first thing you set up is the COM port, and then we carry on with the calibration. Now the calibration page looks a bit busy at the moment, or at first when you look at it, but it's pretty simple when you look at the different groups of controls. First, the right part of the window here is just calculated values. There's nothing you can change. It's just to show you what it calculates and what it measures on the forward and on the reflected ports. On the left side, you have the top group here is the forward or the A port, and the one below is the ref calibration, that is the B port. And you need to tell the program or the device a calibration point for the minimum power and for a maximum power. And let's say that you have a power amplifier or something you're going to measure that will give out 500 watts. It does not make sense to calibrate it at 1 watt and 2 watts because you don't have enough spread from low to high power. So use the lowest power you can adjust and use the highest power or close to the highest power you can. You will get the best response from the device. I will show you in a moment how that works. Below the two forward and reflected, you just have the same meters as you have on the front page. The forward and the reflected and the SWR. You can read the current parameters from the device, and you can write the parameters on this page to the device. This is all that is to the calibration. To give you an idea of how my setup is working, you see on the lower left side here, you see a video running. That's a webcam showing a bird 1 meter and a repam or a dual RF head connected. And I will show you a picture of the same setup. Basically, to the left of the bird, there is a 70 centimeter PA, a small PA module. And after the bird, there is a directional coupler. And you can see the directional coupler has minus 34.4 dB coupling on the forward and the reflected ports. And on each of the two ports, we have an attenuator. On the forward port, I have 20 dB attenuation, and on the reflected port or the bleed port, I actually have 30 dB. Now that is a bit uncommon. Normally you would have more attenuation on the forward port, but it doesn't matter in this explanation. But just make sure that when you use a directional coupler, that you don't overdrive or don't destroy the dual RF head. Let's say that we have minus 34 dB coupling, and I put in 1 kilowatt. I would actually have almost half a watt out here, and that the poor thing up here would not like that. As I said, don't go above 10 dBm. That's 10 milliwatts. So you need extra attenuation almost always. It depends, of course, on your directional coupler, but please do the math and be careful, because you will fry the inputs of the sensor if you do overdrive it. In this case, I have I have 20 plus 34, so I have 54 dBs attenuation, and that is fine for this purpose. I'm only going to drive it with a couple of 100 watts anyway. So this is just to set the scene. This is the test. I have a dummy load sitting here next to the directional coupler, an 800 watts dummy load. So this is the setup, and to get started, the PA is driven by my ICOM IC9700, and I know from I have calibrated the bird, and I know that 0% drive level on the ICOM is corresponds to 31 watts. So the first thing I do is I type in here 31 watts, okay, and I just need to power on the PA. So bear with me just for a second. Now you should, I don't know if you saw it, but the voltage here jumped from 1700 something down to 880 millivolts. This is because there are now power. I think it's about 30.9 watts or anything. I'm just typed 31. I press use. When I do that, I get a warning. It says that the entered watt value will now be transferred to the dBm value field below, and a reading of the voltage from the port will be placed in the voltage minimum forward enter field. Continue. What it tells me is that it will convert the 31 watts to dBm, and it will read the analog voltage and put it in this enter field. I say yes, please. So now it knows that 31 watts corresponds to 44.9 dBm, and the value it read from the forward port was 877 millivolts. Okay, that's nice. So now I go to the ICOM 9700 and I crank up the power to 7%. And I know that in that case, it gives me 210 watts. So I again say, yes, I want to read that. You can see the voltage has now dropped to 698. I say, okay. So now I have this, and now it's calibrated. I just write the data to the device. It takes a few seconds, and now you see I have live data. And I can go now, I can change, go up and down in power, just as we normally would. I can go above 200, and yeah, this works as expected. So this was everything that was needed for the calibration. Now we can measure forward power. And if you're satisfied with that, you can just close it. Sorry, you can even go into settings and say that, oh, I don't want to show reflected or SWR. I just do this. So now I have only the forward power. That's the simple case. In our case, we want to have both. So we enable show pref SWR. And yeah, let me save that so we get both here. Yeah. So the next thing is that we need to calibrate the reflected port. And the way I do it on this setup, because it's pretty simple, I just flip the directional coupler. I swap the in and the output, because then the forward port will become the reflected, and the reflected will become the forward port. And I apply power, and I have of course already done that, and I know that 31 watts on the reflected power, which is the same as 44.9 dBm, will give me 1100 millivolts. And I know that 210 watts, which is 53.2 dBm, will give me 920 millivolts. I write that to the device. And now you see minus 21.6 millivolt per dB, minus 21.7 millivolts per dB. Pretty close. You see that there is a difference between 877 and 1100 millivolts. Why is that? Because as you saw on the directional coupler, it has almost the same coupling factor. But if you remember, I told that the forward port has 20 dB attenuation and the reflected port has 30 dB attenuation. And if you take the 1100 millivolts and subtract the 877, you get 223 millivolts. And 223 millivolts divided by 21.6 gives you 10.3 dB. That's exactly the 10.3 dB's difference in the two attenuators, which is not of great quality. So if it's 10 or 10.5 dB, we're probably lucky if they're that close. But this is the reason why you see that one shows 877 millivolts and the other one shows 1100. And as I said, a higher voltage means lower power, and that fits perfectly with that we have more attenuation on the reflected port. So that's it. That's all that is needed for the calibration. One thing I should emphasize here is that the easier thing is to enter the value in the watt field and press use. It will calculate the dBm value. Actually, the dBm values are what is configured in the device. Everything in the device runs on dBm. So if you enter the numbers without using the use numbers, you always have to enter the dBm value before you write it. Otherwise, it will not know what is correct. So the dBm values will always be used. But the easy thing is, as I did up here in the forward, type in 31 watts, press use, type in 210 watts, press use when you have low and high power on the transmitter. That's it. And then turn around the the directional coupler, and do the same for the reflected port. That's it. So all the data are in the device, and that's it. Now it's calibrated. You can remove the PC program. You can stop it, and the ASCII data coming out of the device will be the correct power forever. Everything is written to the device as we press this right button here. Another thing in settings you can do is under the gauge tab, you can set the maximum value of the bar graph on the main screen, the forward, reflected, and SWR. You can set a warning value. If you pass this value, it will be yellow, and if you go above 600 watts, it will turn red, and so on. You can do that for all the bar graph. You experiment and look. It's easy. One thing is that you can also enter an attenuation value, and if you don't do it, it's not active. But if you do, let's say that from where I measure with the directional coupler, I have 1 dB loss to the antenna. So I type in 1.0 dB, okay? And let me turn on the PA again. I will do just a little bit of power. You see I have 45 watts. If I now click on this one, it will change to yellow and it will show P antenna. You see this? And the 45 watt is what I have calibrated directly at the coupler. So this is actually the power output of the directional coupler. And when I click with the mouse, it will show me what is the power at the antenna. That is 1 dB less. As you saw, I typed 1 dB here. Let me say that, okay, we have 3 dB loss. So now we go from 46 watts to 23 watts. We have half the power. So this is an easy way to show you what the power is expected at your antenna. It depends on what you want to achieve, but it's a feature that is there. And as I said, if you set the attenuation to 0, you can't click it. Yeah, you can, but nothing changes. So it's just an easy way of giving you some more details. Again, on the detail page, you see the power and you see the peak power over here. If I go and give it a bit a swirl, you saw the peak power going up, and a few seconds later it will reset to the current maximum value. So you'll always get the peak power. And remember, all these data here is what you receive on the serial port from the device. The program here just shows the data, the raw data coming in. And yeah, you can update the firmware in the device. Let me, I'm just gonna shut this one down and I can show you. If I press update firmware, it will disconnect the normal update. I can select the file and press download. It will download the file, and once I'm done, I just get out and it will continue working as normal, and you will see a new firmware version probably popping up. You can also log data. You can log data into a CSW or CSV, comma separated file, and you can open the data in Excel or whatever you want to analyze the data. The data are logged 4 times every second with timestamp and everything. Yeah, I think that's yeah, stay on top. If you open some other window, the program will stay on top, and it will not be hidden below any other windows. So that's just a feature. So this is pretty much everything about the program. As I said, go visit Go visit moonbounce.dk for more explanation, downloads, and other projects I've made. One final comment is that the PA that you're seeing tested is actually one of these small devices I have rebuilt for 70 centimeter use, but that's a whole nother story. So thank you for watching, and ask away if you have any questions. Thank you very much.